the Marketing Manager for Innovation Engineering. Before I kick off the webinar and introduce the speakers, just a couple of housekeeping issues. I'd like to ask you to take a look at the settings for your audio in the GoToWebinar interface, and be sure that what you have selected is the audio method that you are currently employing. So for example, if you are on the telephone, make sure telephone is checked. If you're using the mic and speakers, make sure mic and speakers are checked. Otherwise, if you're using two at the same time, it can cause a lot of audio problems. So we'll get into the webinar. I'd like to introduce the speakers. Alan Dubois, the design engineer and our main speaker for this webinar, supported by Todd Coling, the SOC products at Altera, a senior marketing manager, and Stefan Rossinger. Alan? I've just sent Alan a PIN number, and Alan's probably just entering that PIN number right now to open himself up to be a speaker. Hello, Alan. We seem to be having a slight technical problem. If you'll just bear with us for a moment, I'll just send Alan a quick email and make sure he's getting the PIN. Alan, if you can hear me, your audio PIN is number 86. You need to enter your PIN number right now.
Joseph, why don't we go ahead and we can start through the intro while Alan is getting his audio set up.
Yeah, that sounds pretty good.
So this is Todd Kelling with Altera. I'll go ahead and walk through the agenda here, and then Joseph, you can tell us a little more about innovation. So we start with the introductions, and we'll have Alan join us in just a minute. This is Todd Kelling, and also on the line it's Stefan from ARM. We're going to look at this case study today that Innovation put together, which compares a traditional FPGA engineering design flow to one using an SoC FPGA. They did some great work here looking at both the ARM and Altera design and development environment, looking at the system architecture, risk mitigation, system integration and bring up, as well as achieving customer satisfaction through really understanding those requirements.
Excellent.
So we're going to walk through those things at a high level, and then we'll look at the video pipeline case study.
Great, and I believe Alan is with us now. Alan?
Yes, I am. Can everybody hear me okay?
Sounds good to me.
Sounds good. Okay, sorry about that. I was online. I guess nobody else could hear me. Okay, so I'm Alan Dubois, and it's always exciting when I do webinars, as you can see. I just want to quickly introduce myself. So I've been with Innovation since 2010. I've been involved in FPGA design since 1988. My claim to fame is I don't think I have gone through 1 year without doing at least one FPGA design. So I'm very happy to be here and having this opportunity to talk with both Altera and ARM. So a quick introduction is what we're going to do now. I'm going to just send, I think, Todd, you've already done your introduction? Todd?
Hold on just a second here, just unmuting Todd. Here we go. Go ahead, Todd.
Yes, I'm back.
Sorry, Todd, you did your introduction?
Sure. Yeah, I'll go ahead and do that now. So this is Todd Kelling. I'm product line manager for the SoC FPGA portfolio at Altera. I've been with Altera for 3 years, beginning with the launch of our first SoC FPGA in 2011. And prior to that, I spent the majority of my career at Intel, along with various other processor companies.
Thank you, Todd. And Stefan?
Hi, this is Stefan Wellinger. I'm ARM CPU product manager, and Cortex-A9 is one of my products. And I've been in this role since 2010, looking after the Cortex-A9, which is being applied by Altera as an example customer, as well as by end customers like Innovation Engineering.
Thank you very much, Stefan. So what we're going to do is I'm going to start by talking about a comparison of the impacts of traditional FPGA engineering design flow. And the main focus that I wanted to establish here, and the main reason why I had put this presentation together, is to address the fact that because of the new SoC style that we're seeing, and I know it doesn't sound like it's new, but with the ARM being inside the fabric and the coherency and data coherency, is that it's kind of like I'm putting out a call there and say we have to rethink of how we put together and we attack system design problems, because now we have a new infrastructure that we can take advantage of. And that's the whole real premise that I'm trying to put together here. So that's in the first section we're going to be covering, and then after that I'm going to apply everything we talked about to a case study that we did, a video pipeline evaluation platform, and I'll present a lot of these points that I'm talking about during that evaluation. So I'm going to start by just saying hello everybody, Nuvation. This is a great company. Main thing I want to mention here is that we're a company, we move fast without compromising quality, and that's the essence of who we are. We have a very strong leadership, and we've done loads of designs, FPGA and board level, every type of design imaginable. So please feel free to visit our website and give us a call. And we have partnerships with Altera and ARM, and have been involved since 1998, as you can see. And with that, I'm going to allow Todd to take over.
So at the heart of our discussion today is the SoC FPGA. So I just want to touch on this briefly, what it is for any of you who may not have heard about it. This is a new class of product which combines an ARM processor, in this case a dual-core ARM Cortex-A9, with our latest FPGA fabric. And the benefits of this single-chip approach are the higher performance, lower power, lower cost, and smaller board space compared to the two-chip solution. And then next, I'd like to give you some background on the people behind the product. Now, if you can go to the next slide.
Yeah, I just did.
So Altera is best known for our FPGAs. At Altera, we have 3 technology centers teaming up to bring you SoC products, software, and solutions. On the left is our FPGA team in San Jose, California, developing the FPGA design and development tools. On the right, we have the System Solutions Group based in the UK. We put all the pieces together into system-level solutions, such as industrial motor control or wireless mobile backhaul. But the group I want to focus on is the one in the middle. And this is the Austin Technology Center, which Altera established solely for the purpose of developing SoC FPGAs. The Austin team integrates the processor cores and develops the embedded software, most notably the Linux OS support. The site is headed by Ty Garibay, who prior to Altera was Director of Engineering for the OMAP products at TI, and he has assembled a top-notch team of over 100 engineers with deep processor experience to develop these products. And I want to focus on this because I think it demonstrates Altera's vision for the future and commitment to the SoC FPGA product line. And Stefan, next over to you.
Yeah, hello, Stefan speaking. So I just want to briefly outline what ARM does. Many of you will know ARM from designing processors, but actually these days it's much beyond processor technology. It's just basically one part where we are with processors really in product, starting from sensors really going nowadays into the server space. So we are in products like, for example, in Altera's SoC, which goes into automotive type application, industrial type application, but also smartphones, tablets, base stations. Those are really applications where ARM is found today. And if you go to the next slide, I just have one slide showing you the breadth of the ARM solution beyond just the processor. So we are, if you look at a smartphone example, we have technology like the Cortex technology, Cortex processors, and those you will usually find in application type processors. So like the Cortex-A9 is an application processor. But you will find us in many other SoCs and technologies, like, for example, in the modem technology, as well as Bluetooth, GPS, power management, and even down to the sensors, as I said before. So we have various technologies like the Mali graphics as well, which really drives GPU as well as display solutions, really down to artisan technology, which is the physical IP layer. So if you go to the next slide, I tried to give you an overview of basically what ARM really delivers, and it really is to our partners really from top to bottom a solution. So we basically provide the underlying physical IP as well as the processor, graphics, and system IP solution, which allows partners like Altera to build their chips based and basically like an ASIC provider. Then they can strip their FPGA logic around it. And of course, on top of that, that is all really backed up and supported by the software ecosystem as well. So ARM really is, of course, very established in the mobile consumer market, and that really drives into all other markets I've been showing you before. So now I would like to hand over back to Alan.
Thank you very much, Stefan, for that introduction. So here's one thing that I really want to focus on, is that it's important that all the pieces of the puzzle come together for us to be able to want to leverage and harness the power of what Altera is introducing here. And one of the things that, for those of you that go as far back as I do, this is not a new solution. This is a much better solution than what was offered before. There was attempts to do this, and part of the heart of why I believe that this is going to be a very successful endeavor is because of the fact that you have a very mature design and development platform. And I'm going to hand that over to Todd.
Yeah, so at Altera, when we set off to do this innovative new silicon, we realized that we need to have great software to go with it to enable it, because what good is the silicon if the software doesn't enable it? And while the GNU tools, specifically the GDB debugger, are very popular in the industry, the little known fact is that the GDB debugger was actually designed for single-core systems and has kind of been stretched out to multi-core. Whereas when we looked at this, we realized that the ARM Development Studio tools were actually designed and architected with multi-core in mind. So we approached ARM to see if they could come up with a solution for handling this unique device. And they developed an ARM Development Studio 5 version called the Altera Edition Toolkit, which is targeted for these SoC FPGA devices. And the beauty of this is that rather than having two tools and two different JTAG cables to connect everything, you can have just a single cable, the USB blaster tube cable, and you can see both parts of the device. So it's what we call FPGA adaptive debugging, and it allows you to see both the processor and the FPGA at the same time. And Stefan, why don't I turn it over to you next to give us some more details on that.
Sure. So if you look at the DS5 solution, the Altera Edition solution, really what it gives you is, as Todd was saying before, the FPGA adaptive debugging solution. That means you can basically debug the Cortex A9 and P-core, the dual core on the and single core on the chip, as well as you can debug logic in the FPGA. So it really, you have basically one common tool that really removes the barrier of debugging between CPUs and FPGAs. So you really only need one tool. And the beauty of the system really is that we have basically technology called the CoreSight, ARM CoreSight technology, that allows you to really synchronize, especially the debug part, between the FPGA and the ARM processor. So basically you can do things like cross-trigger one CPU to one ARM CPU, to, for example, logic on the FPGA, which basically allows you to stop, let's say, all processors or all logic from working, so you can actually have a nice snapshot of the whole system and really investigate any issues you might want to investigate. So it really is technology that really spans across typical traditional traditional ARM processor system. It really spans now into the space where you can have FPGA logic with your own user logic. And of course, it doesn't stop there. The tool basically also gives you the option to generate the register views of your FPGA. So whatever you basically program and design in your FPGA logic, that will be visible in the DS5 debugger. So it's a really beautiful solution basically for that. And if you go to the next slide. I want to show you we basically go beyond just the traditional debug, meaning that you just basically stop your processes from working and you investigate an issue you might have, but it really allows you with our streamlined performance analyzers to also basically analyze the performance of your software in that particular FPGA SoC solution. So effectively, it allows you to do performance explorations using OS counters. So you basically can use a full OS on the Cortex-A9, and that will give you information about the CPU load, about any network memory accesses, etc. And this is all supported basically through our CPU counters. So each of the Cortex-A9 has CPU counters that can count things like clock cycles, instruction, TLB misses, etc. So that really allows you to get the best performance out of your solution. And yeah, we have debug tools. So Altera offers their USB Blaster 2 solution, which comes for free as a developer. And of course, if you want to take it a step further, ARM offers their D-Stream solution, which basically allows you to have a full elaborate debugging and performance analysis of your system. So I think this slide I hand over again.
Thank you very much, Todd. So Alan, back again. So what I'm going to do is that a lot of this that I'm covering here will be actually covered during the case study. So I'll just go through the slides a little bit quicker. I'm not going to read everything. So I just want everybody to know. So just quickly, the point that I want to make here is that what's really nice is that because now we've got this architecture, what we want to do is that we want to get our customers to be aware that, hey, look, there's a new approach. We don't have to take traditional approach. So what we'll do is that we profile and we assess exactly what the client's requirements are, and then we take a look and say, yeah, you know what, this would fit beautifully in an SoC. And the beauty of this is the fact that you can save a lot of time and money and risk mitigation by not having to commit early on to a lot of high-speed interaction between, let's say, an off-chip CPU and FPGA. If you take a look here, the tight integration between the HPS and FPGA fabric of 125 gigabit per second is incredible. The other thing too is that you can actually tap and have the interaction between the FPGA and the ARM to be actually very dynamic. So you don't have to commit early on, and that really allows you to do a lot of parallel cycling during the development of the project. I'm going to hand this over to Todd to talk about.
Yeah, in terms of the design tools, the key thing here was really to keep tools that people are familiar with, traditional interfaces, and tools that they're used to using, not making a big new hurdle to go over. So for both the hardware engineers as well as the software engineers, that was our goal on the flows. So on the left-hand side, you can see the hardware development. This is using our standard Altera FPGA development tools, specifically the Quartus 2 as well as the QSYS system integration tool to piece all the blocks together. Then on the right-hand side, we have the software development flow. This uses a standard Eclipse-based IDE, and of course the ARM Development Studio 5 program is great for using this, as well as the GNU tool chain, all the standard OSs, and so on. So you've really got tools that both the hardware engineer and the software engineer are very familiar with. Then the key is to link those two together, and that's the hardware to software handoff. And that comes from the Quartus 2 files and the QSYS files. We have that all set up so those files can easily transfer over to the software development environment, and the software programmer can just program as usual.
Thank you, Todd. So what I wanted to talk about, so in system architecting, here's a typical Nuvation methodology, and I talk about we move very fast when it comes to doing development and things like that. And there's two processes. We have prototype process, and we have IDM, which is for design for manufacturing. So here's an example of our process for the methodology for designing a prototype. And one aspect that I want to mention here is that the fact that you don't have to commit early on allows us to have more parallel processing in what we call our phases. So we can do some board bring up phases. So we have some early development that we can actually start without having to commit. We're going to see that when I do the case study, so we give a better example of that. Again, here's an example of IDM. Having that ARM processor inside there and all the hard IP will really allow us to take advantage and be able to implement many of the methodologies that's found in IDM that normally would take additional effort. That we'll actually see there'll be some really nice overlapping abilities to be taken advantage here. So again, just talking about the data coherency, and this is where the key is. This is where we can really take advantage, but we have to be able to do that early on in the system architecting. Todd, you want to talk about this?
Yeah, so while there are many benefits from the integration of the single chip in terms of the performance and power and so on, there's actually times where you want it to behave like two different chips. For example, the power-up sequence. Maybe you want the CPU to boot first and then the FPGA, or vice versa. Maybe you want the FPGA to boot first and configure and secure the system first and then bring up the CPU. So we actually allowed that in this, this chip. So we really thought through when we architected the chip, what are the use models, what are the data flows that are going to be optimum for each of the different applications.
Go ahead, Todd.
Okay, go ahead. That's all.
Yeah,
let's go over to Stefan for on the processor system.
Yeah, so when you look at the Altera SoC, it's really an exciting system. So it basically consists of the hard processor system, which I will talk more about, and the FPGA logic, as well as external interfacing, which Todd is going to be talking more about. But if you look into the HPS system, it basically is a hardened Cortex-A9 system, like what we see today on any traditional ASIC. So it really is basically a full-blown processing system consisting of either single or dual-core Cortex-A9s. And in terms of the processor, it of course comes with the Neon technology, which is basically acceleration technology for things like video, audio codec, decodes, as well as any other industrial applications you might want to use it for, as well as floating point unit, of course, is absolutely standard these days. As well as it has, of course, caching structures, so the L1 caches in Cortex-A9, as well as the L2 caches. And as Alan was saying before, the beauty of basically this dual-core or single-core system is that if you have two cores, you basically have a full coherent software subsystem within the Cortex-A9s. So basically, it's backed by our SMP technology, symmetric multiprocessing technology. And when you go beyond that, Altera has put together a really nice system, basically supporting all kinds of I/O. So, for example, GPIOs, I2C, Ethernet, USB. So, all of really very important I/Os are coming directly out of that HPS system, and of course also the connection to the FPGA. So, this is really where the FPGA logic, where you as a user can basically program your own user logic, and of course interface into the HPS system. As well as on the external side, I'll hand over to Todd, will talk more about the external connections from the SoC into the external system.
So on the FPGA side, there's additional hardened peripheral logic, such as additional memory controllers, also a hardened PCIe interface, as well as various transceivers of different speeds for any high-speed interfaces you might have there. But the other exciting part about the FPGA logic is that if there are any peripherals that are missing, well, you can customize this device to be exactly what you need. So you could add additional Ethernet ports or additional USB ports, whatever you'd like to do. And that's what makes this really a customizable SoC.
Thank you very much, Todd. So, yeah, I lost a little bit of time at the beginning, so I'm just going to, as I said, all of this I'll be covering in the case study here, risk mitigation. And one thing that I want to mention is that having that processor inside there and having that data coherency will really allow and lends itself very nicely to what we call a stepwise development into integration process. So, you know, part of risk mitigation is being able to stepwise enable things and test things out, whether it's a board level aspect that you want to make sure is working. So because of the power of the processor, there's a lot of elements within the FPGA that you can actually bypass and have the ARM processor using a Linux environment to be able to do some, smaller aspects of the design. Let's say for a video pipeline, maybe you'll do 720p instead of the 4K video that you want to do, but you can establish that whole flow and be able to show to the client that, here's the board is working and we have a sample design, and now we're going to kick in the FPGA and, in another week and stuff like that. So that's part of the beauty of being able to have that coherency and how it does have a nice impact in risk mitigation. So talking about system integration, and bring up a little bit of what I was talking about as well for risk mitigation. It allows us to help the client. We've been doing that non-stop for many years, but this allows us to have more ability to add board bring up aspects of it where we can actually have more functionality and not have to spend basically weeks trying to map that out in architecture and design it in RTL. So here's an example of a company that I had bumped into last year, and this is a third-party company that basically is doing what I'm talking about here. And what they do is that they do hardware acceleration, and you hear about this a lot, where you can get FPGA hardware accelerations for simulation. But what they're doing is that they're actually doing a lot of test vectors, and they're using a whole environment that they came up with. And this kind of power that you're seeing here is what's available, and with a Cyclone 5 SoC, you can put in this kind of concept into your design, and you don't have to do it right away. You don't have to commit into it right away. If you're doing an IDM, it's something that you would want to consider, and you don't have to commit to it. So just lastly, because I want to try and get to our case study, and we're talking about achieving customer satisfaction. And one of the aspects that we see a lot is customers, they want to see milestones being met and things like that. By being able to have a higher level of abstraction for data input, such as I mentioned, the video pipeline, or you want to see some video coming out and things like that, and we're hitting some milestones, we've got our auto white balance working, is that you're able to do that. So the case study actually will talk about that as well. The other aspect too is the what if scenarios that you would see. Let's say you get potential corner cases. So here I have an example where we actually implemented it. So this is actually an example of using a processor and an FPGA, where the FPGA manipulated the data that the processor was going to see, and it was a very hard to debug case. The manufacturer couldn't shut down their processing, so what was happening is there was an optical glitch. And so what we see here on the bottom is OZ misalign, is actually the optical glitch that was controlled in software, and it ran through the upper layer software to see if there was a way that they could handle this glitch and bypass it, because they couldn't change the hardware. So that's an example of what I was talking about. So again, talking about reliability, which is we can add more stuff. As you raise the level of abstraction for the amount of effort that you put in, you can get more bang for the buck. So being able to take advantage of, let's say, the Linux environment and putting software routines there is a lot faster than having to manipulate RTL code. All right, so what I wanted to do is I want to concentrate really on this case study. So everything I just talked about with Todd and Stefan was actually leading up more or less to this. So this is an actual design that was done on an Altera Cyclone 320K. So it's a pretty large device. That was done a while back, so we didn't have the SoC at the time. But it's a perfect case study where we've actually had some newer designs where I suggested, hey, this is a perfect SoC design, and this is an example of one as well. So this here has all the numbers. We did it in 17 calendar weeks. It was 1,600 engineering hours. So it was quite a large project, and we took advantage, or we had to take advantage, of a NEOS 2 embedded soft core. So there was actually two boards. I won't be talking about the first board, but I'm using it in the case study because of we have all the timelines and time frames and efforts that we use to develop this product with the client. And the FPGA Cyclone 3 board is the one we're concentrating on. And actually what that was is a full video pipeline. And I'll get into a little bit more details over here. So here's the development and debug tool chain based on mature systems. So now I'm going to just talk about the tool flow. So on the left-hand side in gray is a Cyclone 5 SoC compared to the FPGA-only solution. So the FPGA-only solution required that we did a NEOS, but because we were using a NEOS, doesn't have the horsepower that an ARM does. So we really had to spend some time to architecture it properly, to find out what the custom user interface that the client wanted, and they wanted a custom user interface on a Windows platform. So we had to develop, and we literally spent, I would say, over 90-something hours. We'll see that in the template later on, just to be able to nail that information down so that we could actually start doing the coding for both the FPGA as well as the software. And so one aspect that I want to mention here is that the fact that in the Cyclone 5 SoCs that you already have Linux, you already had Ethernet, we wouldn't have had to worry about this configuration between the custom user interface and the NEOS and the PC. So that was one aspect of the design flow. Hardware or software design partitioning. So we already had a good idea of how we were going to partition it. However, as I mentioned, there's a considerable effort that was required on the initial architecture. Because of the fact that we have a NEOS, we didn't want to have an external processor. The NEOS could do it, but we knew it didn't have a lot of horsepower, so we really had to sit down and partition the architecture a lot. This is a no-brainer for the SoC. So that would have been quite an easy effort to do that. So here what happened is that it delayed a lot of the initial phase work for the FPGA as well as for the software. So talking about the integrated hard IP, so not only talking about the ARM, but we're talking about the integrated peripherals that surround the ARM, and that also includes the memory. So in this design here, we had two soft core DDR2 memories. And what happened is that because of the design, was actually quite full. It was about, I don't know, 70% when we were adding all our testing and all that. It was actually difficult to meet timing for these DDRs. And so it didn't mean we couldn't do it, it just meant it required more effort. So we had to go back, do a little bit more, placement constraints and what have you. So it takes a lot more effort to do that. So when you think about replacing that with hard DDR IP, it makes it a lot easier. So here again, just talking about the more hard IP, and as was mentioned earlier by Stefan, he was talking about the I2C and the SPI. Well, lo and behold, aren't we using both the I2C and the SPI in this design? And so what happens is that, well, not only is it nice to have the hard IP, but you also have to take into account that you have to write the NEOS 2 drivers for that as well. So, maybe it doesn't take a long time, but it takes time, and you have to debug that and all that aspect that surrounds when you're developing new software, and also because it's an FPGA core, it takes up resources and all that stuff. So the beauty here is that this solution would have just had us use the Linux, and that's already built in. And just as an example, one of the projects that we did, which used both I2C and SPI, we got that up and running in 2 hours, and we were talking to our devices and things like that. So it's just something where the choice of the peripheries, the hard peripheries that was selected by Altera for the SoC, I think really hit a lot of common design elements that you'll see out there in the marketplace. Here we have another thing. Now this is really interesting, and what actually happened here is that the client was counting on using USB 2.0 to be able to transfer the data across. They wanted to do some video captures and stuff like that. And the problem is that the USB didn't work properly. And of course, with the Cyclone 5 SoC, Ethernet using Linux was a slam dunk. I mean, that is the way you do it. Unfortunately, here using the USB, and we have to do a lot of custom work. And I shouldn't say we lost a lot of time. That was the elements of that design. Whereas with the Cyclone 5 SoC, just using the Ethernet, being able to harness or take advantage of pre-existing and pre-qualified coding would have just been so easy and cost very little effort and money for the client. So here what I did is that I'm going to compare the actual Cyclone 5 with the Cyclone 3 design. So we took the design and I actually put it through the Cyclone 5, and what we have in the Cyclone 5 is that it doesn't even use the largest part. And so this is quite a significant part in the Cyclone 3. And so in terms of routing and placement and all that. All those we're not seeing here, but it takes a lot less time to do that. So here I am, I'm just actually taking the design and taking a look at which device it actually fits in. And a lot of these are package compliant. And so typically what we would advise customers is for some prototypes, we would go for the 5CS-EA5 for prototyping, as well as have in parallel another prototype board with the smaller device, so that we don't have to deal with trying to squeeze anything in, or if there was some inadvertent things that we'd wanted to add some more features, that we'd be able to add that. So some functional requirements. So as I mentioned, there was some image capture that the client wanted, and the image capture rate was actually quite slow because they ended up having to go with a custom interface, and so the customer would have really liked to have increased that, and there was no physical way that we could increase it. So that's something where if they had an initial requirement, we met the initial requirement, but later on they went, oh man, it would have been just so nice if we could have at least doubled it or 4 times that. Whereas with the Cyclone 5 SoC, it would have been about 30 times faster than what they had asked for initially. So, and again, talk about unforeseen changes in external requirements. So the USB 2 port didn't work, so they had problems with that. So we had to scramble and then help our client with that. There was an off-the-shelf board that they had selected, so they went with a GPIO. So there wasn't a lot of options that we could do. And again, with Cyclone 5 SoC, we wouldn't even be talking about this slide here had we been able to select that part for this design. So further cost savings in terms of co-verification, real-time debugging. The video frame work that we did was a custom design video processor, and it was quite significant. It was very modular and things like that, and like anything, it took a while to qualify, get all those corner cases. So there's a lot of elements of the video pipeline that were difficult to debug, just because a lot of the debugging, you can imagine simulation flows, how long that takes for an FPGA, never mind an ASIC. And so what happens is that you have to do a lot of onboard debugging for corner cases and things like that. So what happens is that with the ARM, the power of the ARM, you're able to actually put in a lot of these test vectors, a lot of these test patterns that can be utilized to test some of these very difficult test cases. The auto white balancing was actually quite challenging. Sensor raw data and raw data interface was also something that the original specification and board from the client didn't work. So we had to actually write our own interface for that to mimic it. And it would have been just so much easier to use the ARM, because even with the NEOS, we weren't set up to do something like that. So here's an example, just a partial block diagram of what I'm talking about. So this is the design that was implemented. And if you take a look at the flow, and what I'm talking about here in the flow is that the beauty of an SoC, the beauty of the data coherency, is that at any point in time, even that test pattern, the DDR controller, is that we can actually utilize the ARM to implement some test patterns and a lot more elaborate at a much higher level of abstraction, and the amount of effort to do that would have been minimal. Okay. So here I'm just profiling some of the numbers here. So for 1080p 60, so we're just taking a look at different data rates. The one that we actually ended up doing was the 36-bit. So the example that I'm showing here is that the final design is 1080p 60. It has quite a high bandwidth and a lot of the processing, as we can see. Sorry, I'm just going to go back one slide. As we can see in the video pipeline. So what the point that I was making is that using the ARM, we don't have to go at the highest resolution. We could use a subset of that resolution to be able to qualify a lot of blocks, as well as to help unblock, let's say, the customer that was doing the user interface part of it. And until everything is ready, it was difficult to be able to do some early releases for the client. So that was a focus, but it was still, there's a lot of debugging involved here. So here I'm just going through a lot of the numbers and just showing an example. If we take a look at the fifth bullet, example below shows a full frame of video at the lowest rate. So in this example here is that using the DDR3s, and I was using something like 50% efficiency. Us at Nuvation, we typically get over 85% efficiency for our data flow to and from our DDR interfaces, and I just wanted to show even with 50% efficiency that it would have been very, very feasible to use the ARM core and its power to be able to implement a lot of the test patterns. And the example here is it allows the ARM 26 milliseconds in the 30 frame per second requirement. So the things that we can do with Stefan, the ARM is unbelievable with that amount of time. Would you agree, Stefan?
Yeah, so I mean, just a question on this in terms of frequencies. What sort of frequency differences did you have on FPGA only versus the Cyclone 5?
Yeah, so typically we kept to the same frequencies, and actually I'll just go up quickly to the case study here. So typically we kept the same frequency here. So because we're using typical video rates, it was like 150 megahertz in that range. So those were the typical frequencies we're using.
Right.
And
but I guess timing was easier to reach because of the hardened HPS system.
Yes, with the Cyclone 5 SoC, it wouldn't have been an issue whatsoever. You know, and the DDRs were running at over 200 meg. We had to compromise and go down a little bit for functionality, and we calculated everything just to be able to, you know, lower the amount of effort that you're going to put into trying to do time enclosure, as opposed to it didn't really impact the schedule. You know, even let's say for doing frame capture and stuff like that had very minimal impact. So, you know, we opted for that, which we wouldn't even had to for the Cyclone 5. So you're right, the frequencies would have been quite something, you know,
right.
to use the highest frequencies. So here we're just going to move on into you know, incorporating the trade-offs. So let's evaluate what we see between using the FPGA only, and this is a traditional approach as opposed to an SoC. And again, just want to remind everybody that the real focus I was trying to bring out here in the presentation is to say, hey, you know, let's rethink the way we architect. Let's rethink the way we attack our problems. Let's take advantage of the SoC. These designs are real. The tools are real. Absolutely true. It took me a day and a half learning curve installing the tools to get sample code going through the first time when I saw this tool, and I just said, yeah, this is perfect. I'm familiar with all the tools and things like that, and there was absolutely nothing new. It only took a day and a half for the licensing, though, so I won't talk about that. So here is just an example, and what I have in this sample here, and I'm going to finish off very quickly, just to allow people to ask some questions. And we have the engineering hours, and what I have here is the ARM estimate versus the actual NEOS. So as far as the, if we take a look at what's highlighted in gray, the controller firmware spec, the spec took us a total of about 94 hours, where the simplicity in what we would have done using the Linux environment would have almost halved that. Similarly with the LDD, which is Nuvation's term for logic design description for our FPGA, because it had a huge impact on what we were implementing, we had to do RTL code to be able to interface to the NEOS. So it was custom interfaces for the NEOS in terms of that. So that also would have had a positive impacts on there. The other phase one total, so that's when we're actually designing everything and specifying everything in our logic design descriptions, our software design descriptions, and what we do is that we start implementing everything, and you can actually take a look at the reduction is throughout in both the coding and our simulations and everything like that. So it has significant impact being able to take advantage of the SoC. So in total, I just want to show on the left-hand side is that in terms of effort, in terms of cost, we see a reduction from 17 weeks to 12 weeks, and in terms of hours, that was a reduction at 65%, so 30 and 35% of both calendar and effort. So it's quite significant when you're taking a look at the benefits that the SoC has to offer. So I'm just
Alan, one
highlighting
question
that.
on that one.
Yes.
On the ARM column there, does that assume any FPGA design reuse, or is that all from scratch?
That's an excellent question, Todd. This is all from scratch. So today, if a client would ask us to do that, we have all this IP that we're talking about in this example. This is all Nuvation-owned IP. So these numbers, a lot of them would actually be 30% of what you're seeing here.
Okay, it'd be even better with IP reuse.
Even better because of the fact that we have existing IP. Yeah.
Great.
That is correct. Thank you. Thank you for the question. So for testability and reliability, I want to give people an option to ask questions. So again, I'm just showing that there was additional effort for us to be able to have some additional testability. The one aspect, and I'm sure everybody out there would agree, is that the key thing that we really, really would love to do is we would love to bring the abstraction level as high as we can, but maintaining the optimal implementation. So there's been a lot of effort throughout the years of, hey, just 20 lines of code, you can generate this whole video pipeline. That's the ultimate goal. What I'm saying here is that by using the ARM SoC, you've already brought the level of abstraction a lot higher. So creating test pattern, if I need a JPEG encoded test pattern or what have you inside there, and we actually have had that project where we'd have to implement all that in our tailing, just didn't warrant the effort to be able to do that, So instead you try other things. But with that kind of level of abstraction, say, oh yeah, you know what, that's maybe about 3 hours work for us to grab a little JPEG thing. We already have the interface. We already know the communication, the data coherency is there, no problem. Let's test that out and let's see how we can handle that decoding and stuff like that. So that's one of the things that I want to really point out here is the fact that we have a high level of abstraction going up, and it makes it a lot more viable to do a lot more testing, okay, abstracting the FPGA details. And I think what I'm going to do is I'm going to thank everybody for the slide presentation. I'm going to hand this back off to Joseph, and I want to allow people some time to pose us some questions. Joseph?
Thank you, Alan. Pleased to say that a lot of people hung on all the way through this presentation, so I think it must be offering some value. I'll just get right into the questions immediately. The first question is from Dave Mahoney, and he asked, is the mask for that is presented able to turn on and off options for the different COM features in order to add more UART channels by removing DMA or CAN?
I think that's a good question for Todd or for Stephen.
Yeah, I'm sorry, you're going to have to repeat the question there and follow the details on that one.
Okay, and you should be able to see it now in your panel as well, Todd, so you can read it. It's a very read kind of question. So the question is the mask for that is presented able to turn on and off options for the different COM features in order to add more UART channels by removing DMA or CAN?
Yeah, I'm not sure what's meant by the the mask on this. It's not like an ASIC where it's taped out differently. You would in the FPGA fabric, you could build your own additional UARTs or DMA channels.
Okay. The next question is, will these parts be a short-term offering like the Excalibur devices? I figured the part is Altera, so I pitched that over to you, Todd.
Okay, yeah, that's a good question. I appreciate you asking that, Stephen. No, they will not be. But first let me explain the Excalibur devices for the rest of the audience who may not be familiar with them. Altera did attempt a product like this before my time, probably about 10 years ago, that integrated an earlier ARM processor along with an FPGA. And it was really a product that was just a little bit before its time. Back in those days, the processor space was still very fragmented with players like MIPS and PowerPC still out there in addition to ARM, as well as I think the tools weren't quite mature, as we talked about today. And last but not least, the pricing wasn't there. I think there was value in this integration, and so the prices are actually priced higher than the current, the combined solution would be. So now today, obviously ARM has become the de facto standard. I think the tools have matured. The pricing, we've actually priced it to be more attractive than the standalone parts. So I think it's an idea that time has come, and we're really getting great acceptance for it now.
Great, thank you.
And I would point out that we're still shipping Excalibur to the people that did use that. So even though it was like a one-time device, we're still shipping that 10 years later to those customers, showing our commitment to the product, and those people are now moving to the SoC FPGA.
Thank you. The next question is from Renee Bouchat. With the tools, will it be possible to debug NIOS 2 and the two ARM processors together?
So
and,
the first solution, if you look at it, is basically for the ARM processors. It will basically allow you to connect into the FPGA logic. But I believe, Todd, you guys have a separate solution for NIOS 2 to debug, like the GDB, etc.
Yes, that's correct. So you can indeed implement the NIOS 2 along with the SoC FPGA, but then the debugging would be slightly different.
Yeah, the debugging is different, but I can tell you right now is that we've actually done stuff like that where, because I'm more of an FPGA guy than the firmware guy, and we're not always working together closely. So what happens is that I'll actually implement a lot of, let's say, the NIOS at a higher level, some of the control signals, and I'll get that to trigger something or what have you. So there's a lot of flexibility there.
Thank you. The next question is from Albin Takemi, and I think this is one for you, Alan. If the video processing implemented in FPGA blocks uses most of the capacity in the system, what do you need the high-performance ARM Cortex-A9 for?
Right. So one of the things is what happened is that the ARM Cortex-A9, we had some video pipelining. We had some what we call the doing captures, video captures. And so the video captures, how would we get that across to the PC? So what the ARM was doing is doing the communications between the PC application and the FPGA, the video pipeline. There was a lot of setting up you had to do. There's some auto white balancing settings. There was some control settings for the other board that we had to do. So there was a lot of housekeeping. And then, as I mentioned, by using the ARM, we could have utilized the Linux system and Ethernet, and we would have been able to go at full throttle with the Ethernet. Trying to use, let's say, just a NIOS for Ethernet, you just don't get full bandwidth. You wouldn't be able to do gigabit and things like that. So with the ARM core, we would have been able to do that. So that was used for the user interface part of it.
Thank you, Alan. The next question is from Renee again. Will OpenCL be available for this architecture directly without PCIe interface? I think that's one for you, Todd.
Yeah, I can take that one. Yeah, I'm not sure what's meant here by without the PCIe interface. I don't know that there's really any dependency on that for the OpenCL. But I will point out that we do have an OpenCL SDK toolkit available today. It supports the SoC devices, and we plan to support all the SoCs with that. On our website, there's also a great ray tracing demo that I would encourage people to look at. So OpenCL is definitely something that Altair has been very proactive on, and just like SoC FPGAs, we see OpenCL as being a great part of our future, and the marriage of those two is very powerful.
Thank you, Todd. And the next question is for you as well. A lot of interest here in the product line. When will the ARIA 10 dev kit be available?
All right. First, let me explain what the ARIA 10 is for those who may not have heard of it. But the ARIA 10 is our next generation SoC FPGA, and it's at a 20 nanometer technology, and it will run at a 1.5 gigahertz processor system. We decided to keep the same dual-core ARM A9 because the dual-core ARM A9, frankly, is very powerful and meets or exceeds many of the needs today. And so by moving to 20 nanometers, then we get a performance boost as well as a power savings. Now, in terms of when the dev kit would be available, that's looking like early next year is when we'd have the dev kit for that. But I would point out, because it's the same processor subsystem, you can actually begin development with the ARIA 5 SoC dev kit today, and then that code would immediately transfer to ARIA 10 dev kit when it's available. So I think don't wait, get an ARIA 5 SOC dev kit, and you can start today.
Okay, terrific. And another question for you, Todd. What is Altera providing? This is from Nicola Tragic. What is Altera providing for the customization of hardware IP blocks?
Okay, yeah, another good question. So to some degree, you can use the OpenCL for translating your C code into the parallelized code and kernels for the FPGA. But more so, I think the key to answering this question is the QSYS, system integration tool. So you can go off and you can design different hardware IP blocks in VHDL, Verilog, whatever your preference is, and then you can abstract as that a block into the QSYS, and then you connect it up to all the AXI buses and everything in the QSYS environment. So the answer to that question is really take a look at the QSYS system integration tool.
Okay, thank you. And the next question, I believe, is a good one for you, Alan. Why is the pin map and top-level HDL ports needed for HPS IOs? Aren't those signals hardwired, or is there some kind of programmable interconnection network between HPS and actual chip pins?
I have to say I have a huge smile on my face. I was just reading that question before you read it to me, and I said, wow, I really would like to hand this off to Todd, because the reason why is because that was one of the first questions I had when I saw this device come out. Todd, would you be able to grab that?
Yeah, so the answer is there are various pin muxing schemes on the HPS peripheral pins. There's basically like 4 sets, four combinations you can use. So you do need to dig into the data sheet a little bit to make sure that the specific combination you want is available. That's maybe the difficult side. The good side is you can actually route and share I/O pins with the FPGA, so you can actually go out through the FPGA up through the HPS or vice versa in some cases. So there's flexibility, but it does take a little bit of work to dig in and make sure that the traffic you want to see is possible.
Thank you. I'm not sure, by the way, if we're going to get through all these questions in the time we have available. I'll keep going, but if we don't, what I'll do is I'll collect the question from the individual, and we'll actually try to have somebody follow up with you and actually answer your question. So I really appreciate you taking the time to come here and pay attention and ask these questions, so we're going to certainly extend you that courtesy. So the next question is from Philip Van Hoot, and it is one for you, Alan. Is the FPGA part of the SoC purely a slave, or can the ARM's memory map be shared with the FPGA? How easy or hard would it be to implement Ethernet offloading such as UDP encryption or synchronization points between Linux and NIOS, for example?
That's an excellent question. Thank you, Philip, for that. The FPGA can share actually the memory map. So when we talk about the memory map, it's really, depending on what the memory map is, there is a way in the infrastructure, and even Stefan, you'll have an opportunity to either quote me or tell me I'm right or I'm wrong, but there is actually a way, depending on what the elements are, because in the periphery, some of these elements can be memory mapped. There is a way, there's a bus that allows the FPGA to share almost all the periphery with the ARM, and so you can do that. I haven't done that myself, but I know it can be done, especially for the memory mapping and the DDR and stuff like that. That can be shared with. Really nice is that the dedicated DDR is not, memory controller is actually not just for the ARM core. Is that the actual FPGA has a path through that, through one of the cache lines. So that's really nice. So the answer is yes, absolutely, for that question. The next question is how easy or hard would it be to implement Ethernet offloading, such as UDP encryption and things like that? The answer is actually quite simple. Because of that data coherency and being able to share, that's basically co-processing. So that's what we've been doing for years and years and years, is adding co-processing abilities between an FPGA and a microcontroller. This makes it a lot easier. So the answer to that question is absolutely, that can be done quite easily.
Thank you. And I think we have time for one more. and I don't know who's going to want to answer this question, so I'll just read it out and you guys can jump for it. The ARM CPU will have to share the controller interface to the, oh, it's from Mehdi Tabouri. The ARM CPU will have to share the controller interface to the DDR with other video pipeline blocks that need to access the DDR, such as frame buffers and filters. What is the impact of using ARM CPU and its bus, reading and writing to memory, on the performance of the system compared to the impact of using NIOS 2 and its Avalon bus?
I can answer that, Stefan, if you want to.
Go ahead. No,
you haven't had any, so. But I can't tell you that.
That's fine. You guys are doing a great job.
Okay, so in the profiling example we're talking about that there was 2 DDR controllers, and one of the DDR controller for this video pipeline was reserved for actually just doing the video pipelining. Then we had another snapshot DDR controller, and what I did is that in the DDR control space, and I took a look at the how much overhead it would take to be able to talk to the DDR. So when you put the code, depending on where the code is, if you put and how big the code is, so for running Linux and stuff like that, is that the majority of the time is that the ARM will be using that DDR memory. The pipelining is a snapshot, so depending on what the requirements are for how fast we need the snapshots and things like that, we can squeeze that in very nicely through arbitration of the bus, and that's handled automatically in the QSys system, so you'll be able to automatically put that in. So in terms of RTL effort, it's very low. Whether we use a NIOS or we use the ARM, the concept is identical. That's the beauty of it. So for a lot of those that are familiar with using NIOS and DDRs and stuff like that and sharing memory, we've done several design where the processor memory is using the DDR as well as storage memory, and we're sharing that. That's the same concept here. There's actually no difference.
That's great. I think we're going to have to stop it here. I am going to answer one question, which was to me, and a couple of people have asked me already. Everybody who's attending the webinar will receive an email shortly within the next day or two with a link to the video version of this webinar so that you can access it and take more time to review the density of the slides that Alan presented and review everything. There are some questions here which we have run out of time, so we're not going to be able to answer. And as I said before, I'm going to collect those questions and we're going to follow up with you and answer your questions. So I hope it was a good webinar for everybody, and I'd like to thank you so much for coming. Most of you stayed through the entire webinar, so I hope that means that it was very interesting to all of you. And I look forward to doing this again with the engineering community. And thank you so much, Todd, Stefan, and Alan, for the time and energy you put into making this presentation for everyone.
It's a real pleasure. Thank you.
Thank you.
Yeah,
Bye-bye now.